So you can get the answers, verify the answers for me, though I do have an answer. So, okay, the first question would be a feeder power 5 kW cooking units. So this is a feeder that feeds cooking equipment. Can you guys see there's 5 kW and 7 kW and 11 kW range and 16 kW range. The power system is 240/120 single phase. Find the following. Has 8 points. Feeder ungrounded conductor size. Feeder grounded conductor size. The ungrounded is the hots. Feeder grounded conductor size. That's what we did yesterday. Feeder overcaptation device size. And then we need the branch circuit ungrounded conductor size for the 7 kW range, as well as the grounded, the neutral. We need also one for the circuit breaker for the 7. And also we're going to do the same thing for the 16. Can you guys see that? So the branch circuit, we need to size the branch circuit for the 7 kW and the 16 kW plus the feeder. Cool? So that's question number 1. And then we'll go to question number 2 in a second. Okay. Here's the diagram. Here's my expectation and your expectation, guys, from all of us when we design a power system. When you design a power system, you're looking, the first thing you're looking at a power coming in. So A, I call this is A. This is the feeder that you need to size. Then B is the neutral. A is the hot, B is the neutral. Cool? So A will be the hot, B is the neutral conductor for the feeder. Then C is the circuit breaker for the feeder, right? Does it make sense, guys? Bringing the feeder to the circuit breaker, the main panel. Then when you go down here, I would like you guys to size, same thing, branch circuit, which is D, the hots for this branch circuit for this 7 kW, as well as a neutral. And also, F, I need you to size the F is the circuit breaker for this 7 kW. And I want you guys to repeat the same thing for the 16 kW. For the 16 kW. Does that make sense? So when you size this branch circuit here, and this one, as well as the feeder. And don't get confused between the A and the B and all this stuff. These are just illustration to get you to understand. So I have 5 kW cooking units. I have 7 kW range, 11 kW range, and 16 kW range. And you see the numbers, right, is underneath them and the sizes are there. Any comments, any questions about the diagram? You guys have the diagram right in front of you. Any question about the diagram? Because it's so important to understand what we're trying to achieve. We're trying to size a feeder and one feeder right here and 2 branch circuits. So you guys can do it as a homework too if you want to, or exercise. You can size the branch circuit here and the branch circuit here. For the test, I only want you to size 2 branch circuits. Cool? Shall we start? Go ahead and do it. Now, tomorrow you're not going to see this diagram, guys. What you're going to see for the test is you're going to see this text. So get used to it. That's the text that you're going to see. So, and you're going to interpret it into that diagram. That's what designers do, Matt. Cool? We did it yesterday. We'll do it today. So, any comments, any questions before? Go ahead and do it. Comments, Karen, we're good? Okay. Derek, any questions about the diagram? Everybody knows what we're doing. We're basically sizing a feeder, neutral and hot and overcaptation device, a branch circuit, neutral and hot and overcaptation device. Straightforward. Now you need to have your NEC code book handy because we're going to be using the NEC code book. So, okay, so I'm going to start directly, guys. I'm going to start with sizing A. I do have the calculation here for you. I'm going to start with sizing A. So if you look at A, yesterday we were looking at 220.55, the table 220.55. I want you, Matt, to look at these sizes. Do you guys remember that 5 and 7 are under B? Both of them are under B, right? Remember that column that we were looking at, the table? Both 5 and 7 on from table 220.55 are under B. 11 and 16 are under C, column C. So we're going to go apply, find the demand for all these systems. Okay. So the first, we're going to size, the first thing is the feeder. I need to size the feeder. So here's what I would like you guys to do. The first thing we need to do is we have a 12, I want to find the demand for these two. The demand for these two under C. The demand for these two under C. There are more, they're under C and they're different sizes. Do you guys remember what we do if they're under C, different sizes? We find their average and we increase the average 5%. We find the demand, we increase the average, we increase the demand 5%, the average is more than 12, if you guys remember that. So here's what I'm going to do. The first step I'm going to do is I have one range, 12 kW, plus, I need to find the average, plus three ranges, 16 kW. I need to average them, divide by 4, and that will give me an average of 15 kW. This is coming from table 220.55, note number 2. That's what, if you guys go to 250 table, 250.55, note number 2 will tell you if they are more than 8 3/4, you average them and you increase the demand. You increase the demand 5% for every kW. The average is more than 12. Well, I think maybe the best way to do it first is to find the demand for these. So I have how many of them? I have 1, 3. I have 4 ranges under C. What's the demand for 4 ranges under C? 4 ranges under C. The demand for 4 ranges under C. How much? 50%. No, under C. Oh. The kW. 17. Okay, so that's probably should be the start point. So 17 kW. That's for the 4 of them. For the 4 of them, why 4? Here's 1 here and 3 here. 4 ranges under C, column C, give you 17. Then I need to up the 17, 5% for every kW. The average is more than 12. Okay, so then you find the average. Then the next step to do is how far is the 15K minus 12K? That will get you 3K, 3kW. Then you take the 3 and you multiply it by 5%, and that will get you 15%. That will get you 15%. And the last step, guys, is to take 1.15 and multiply it. So my demand, I'm going to call it demand. The demand would be 1.15 multiplied by 17, and that will get you a healthy 19.6 kW. Done. Any comments, guys? Any questions for these 4 ranges? Now, if you can see, this is only for the 16 and the 11. We apply C for them only, right? 16 and 11. We apply C. 1.15 times 17, 19.6 kW. Any comments? Any questions? Any comments? Any questions? So that's under column C. Everybody, can you guys see that? This calculation for only 2 sets of them because you go under C. Okay, Matt, does it make sense? Why did they do it this way and up it? Okay, so now we did this and we did this. Now we're going to go to these 2 sets of ranges and cooking units and apply the table to them. Derek, my friend, can you tell me that, can you see that 5 and 7, both of them are under column B from table 220 to 55 that you guys are looking at, you should be looking at. So I'm going to go, so if it's under B, then I have 6 ranges. How many of them do I have? Can you guys see now? I'm going to go apply the second step. I have 4 and 2. Can you guys see that? 4 and 2 under B. Okay, so 4 and 2 under B. Let's go to, I'm going to write it in green here just to emphasize it. So I have 6 ranges. These are table 220.55. If you guys go to C, can you guys find me what's 2 ranges, 6 ranges under C? What? Hold your horses. First, we find them all together as a C, under C. How much? 43. Thank you. 43 kW. Okay, first you find the 6 of them under C, then you apply the A and B. A does not apply, then and you choose the smallest. So for 6 of them under C, guys, get you 43. Now let's go apply B and see if we can come up with a smaller number than 43. Did you guys see? Let's go apply B and see if we can come up with a smaller number than that. Okay, so for both of them are under B, so what you need to do? So let's say so we're gonna go add them up. First, you need to add them up. So I'm going to demand from the same table under B, because table 220.55 under B. For 6 ranges, guys, what's the demand under B for 6 ranges? The percentage was 43. Is that? You should have given me that one under B. The A under C should be different than the C.
Oh, wait, the first time that would be 21 then.
Okay, thank you. That's what I thought. Yeah, you did it under C. Okay, for 5 ranges, it's for 6 ranges. Thank you. For 6 ranges, this should be 21. For 6 ranges, the demand is 21. 21 kW. Okay, so now I have to go apply B and see, can I come up with a number less than 21? If I can, then that will be my demand for this step. Okay, so for this one, guys, would be, 43%. The demand is 43%. So what do? Then you come over here. You come over here and you take, how many ranges do we have? Let's take the sizes of the ranges. I have, add all your ranges together. I have 2 times 5 plus 4 times 7. This is all the ranges. So if you add them all up, and that will get me 38 kW, 38 kW. And then if you apply the demand for them, so 0.43 multiply, that's the 43%. Multiply this by 38K, and that will get you a healthy 16.3 kW. Now, I want you guys to look at this step. So under C, we got 21. Under B, we got 16.3. Did you guys see it? So which one am I going to use for my total? Which one am I supposed to use for my total? The smallest. So this number here, you compare these two numbers together. Choose lowest. Choose the lowest. And what was the lowest for the two? 16.3. What's the lowest? 16.3. Any comments, guys? Any questions? Any comments? Any questions? Not if you're going to take notes, or okay? Is that how you? Okay. You scared me when you don't take notes. Any comments? Adam, does it make sense? Okay. Derek? Okay, so we got these together. Then the next, guys, what do? You add them together. You add the two. So I have. So this was for this step. This demand was for this step here. I have a demand for the second step. So you can see that. Then I have to add the two together, right? This calculation is for one set of ranges, another set of ranges. Then I need to add the 19.6 for all this, and a 16.3 to get my total. Okay, and that's what we're going to be doing. So then you take. Next, you're going to take the 19.6 kW, add it to the 16.3 kW, and that will get you a healthy 35.9 kW. Healthy 35.9 kW. Gentlemen, ladies and gentlemen, this is your demand load. This will be your demand load. That's what you're going to size your feeders for. And you can see that this is a 19.6 came from the two big ranges and the two sets of big ranges. And the 16.3 came from the two sets of smaller ranges and cooking units. Animal. And when you reach this step, you're done. When you reach this step, my friend, you're done. The rest is history. Shall we? Now we need to size A is, we're still sizing A, guys. This is question number 1A. A is the feeder. We're still sizing the feeder, remember. So then you need to write in here, now we've got your demand. This is my demand. Demand for feeder. For the whole feeder. That's my total demand for the feeder. Now piece of cake. Then I need to find the current. The current equal 35.9K divided by 240 voltage to find the current. And you are going to end up with 149.6. 149.6 amp. This is the size of your service. That will be the size of your service that's coming to this building. Okay? So since we're doing dwelling, guys, then you take this number, 149.6 amp, take this one to 240.6. What's the overcapacity device in 240.6? 150? 150 amp. So this is my circuit breaker. The size of my feeder, right? 149.6 get you 150 amp. Okay? Then you take the 150 amp, take it to table 310.15 B7. Can you guys go to 310.15 B7 and find me the feeder? Why B7? Because we're still doing dwellings. We don't want to go to 310.16. We're doing dwellings. So 150 will give me, what's the size? Anybody can see that?
Yeah.
My size for 150, no. 310.15 B7. B7.
Oh.
The one before it. Just because it's dwelling. Number one. You're right, 3 aught. If it was other than, if the voltage is different, so that will give me what size? As a surface of a feeder, 2 conductors. That will give me 2 conductors. Number 1 THHN. Number 1 THHN. Okay, so let's write it. AWGTHHN. So we went to 310.15 B7 because we are allowed to, because it's dwelling. We're allowed to because it's dwelling. Any comments, guys? Any questions? So what size hot conductor do we need? Number 2. So please, in the past, I used to go to 310.15 B16, but you can, but the code allows you to even go lower than that because it's dwelling. You can go in size number 1, copper, all copper. 150 will give you number 1. So that's the hot. Any comments, guys, about this? Karen, does it make sense? Yes? No? Let's go find the neutral. The neutral, do you guys remember what we did for the neutral? The neutral will be question, the same thing, question number 1B. B is for my neutral. I need to find the neutral. For the neutral, it's piece of cake. You take the size that you get for the neutral, 149.6, that's the 8 amps. multiply this one by 70%. Multiply this one by 70%, you end up with 105 amps. 105 amps. 105 amps. Can you guys see that? 105 amps. Then you take the 105 amps. Then you're going to take your 105 amps. 105 amps. Take it to table 310.15 B7. Take this one, guys, to 310.15 B7, 105. For my neutral, that'll give me number 3. What's the size? Will be one conductor, number 3 AWG THHN. So here's the size of the neutral, and here's the size of the hots. Any comments, any questions, guys? So Aram, the only difference for the neutral is we cut it by 70%. Do you guys remember yesterday? We slammed that 70%, we cut it by 70%. Now your size is our size based on the minimum, then the sequence go. Now we size A and B. Everybody knows where the A and B in the test that you have? We size A and B. The last thing we need to size is C. Can you guys see C? So here's my A. So here's my, we size A is the feeder ungrounded conductor. B is the feeder grounded conductor. Now C is the circuit breaker. Circuit breaker for this system, we already sized it here. Can you guys see that? The circuit breaker, now C, this will be also question number 1, C. For C, what you do is you take 149.6 amp, take it to 240.6, and that'll get you 150 amp. So that will be 2-pole circuit breaker, 150 amp. 2-pole circuit breaker, 150 amp. Listen, does it hurt my feeling tomorrow, guys, if you write yourself a cheat sheet, which table to go to? Did you hear me, Matt? Which table to go to size what? Did you guys hear me? There is a lot of information here, and I dare anybody without a cheat sheet to follow up with it as we go through the whole year. So write to yourself, if I want an overcap protection device, circuit breaker, I go to 240.6. If I need a cable, I go to 310.15 B7 for residential. So that's A, B, and C. We size the feeder. We just got size the feeder. We size the feeder. Now, I'm not asking you to size the conduit for it, guys, but you can go ahead and size the conduit if you want to. I did not ask on the test to size the conduit. So this would be my circuit breaker. The circuit breaker is going to be 150. Shall we go to the branch circuits, guys? Before I leave the feeder, any question about the feeder? Feeder looks at the whole, all the system together. Branch circuit, one range or one cooking unit at a time. That's what a branch circuit is. The feeder sees everything. So if each one of you guys is all of 5 of us, if we're all ranges, if a feeder will feed 5 of us, if it's a branch circuit, one at a time. Each one will have its own feeder, its own branch circuit. We're done with the feeder. Before I leave the feeder, can you guys give me a thumbs up, Chad? Good? Everybody's good? Okay. All right. Adam? Okay. So let's go to the branch circuit. This is question number 1, D. D, it asks you about the branch circuit for the 7 kW. So what I'm asking you guys in particular, would you please find me the branch circuit for 7 kW range? For the 7 kW range. For the 7 kW range. Okay, cool. Now, for 7 kW range, guys, this is a branch circuit, 7 kW range, from table 220.55, and this will be column B, and also note number 4. From column B and note number 4 of that table, it tells you can apply for ranges. You can actually, for ranges, is the 7 kW a range? Is it a range? I thought it was a range, right? For ranges in particular, yep, the 7 kW is a range. For ranges only, you can actually apply the table also to the branch circuit. Did you guys hear me? Not for the cooking unit, just for the ranges only. Okay, so for 1 kW then, this is only 1 kW, one range, 7 kW range.
That was 4. Oh, no, it's 3.
Yeah, one of them, because we're doing branch circuit. There's 4 of them, but they will be identical. You got it? Only one of them. So that'll give you 80%. The derating factor is 80%. So, having said that, then you come over here and you take the 0.8, multiply this one by 7. That will get you a healthy 5.6 kW demand load. This is the demand load that I can size for. Why did I apply the table to a branch circuit? Because it's a range. Because it's a range. Okay. Now the rest is history, my friends. Now you need to find the current, which is I. You take the 5.6K, divide this one by 240, and that will get you a healthy 23.3 amps. Okay? And then, now I want you guys to look at which table do you go to. You take the 23.3 amps. Which table am I going to go to? Can I go to 310.15B7? No. Why? Because it's only for feeders and service conductors, not for branch circuit. So in a case like this, I have to go to table 310.15B16. I can't emphasize under column under 60-degree fill, because the amps are 100 or less, right? So, did you guys find number 10? Under 60 degree? So two conductors, number 10 AWG. Two conductors, number 10 AWG. Okay, so what was the first? So D, branch circuit ungrounded conductor, D, and E, branch circuit grounded conductor. So let's go to branch circuit. So this is D, branch circuit ungrounded conductor is 2 watt. Now, the second thing we need to do, guys, is for the neutral. Now, for neutral, same thing. What are you going to do for a neutral? For a neutral conductor. That should be E. That should be question number 1. That will be question number 1E. Question number 1E. For the neutral, what do I do? You take the 70%, multiply it by 23.3. Can somebody get me the math? I did not have the math for this. 16.3 amps. 16.3 amps. 16.3 amps. Okay. Okay, so then what's the what conductor size do I need? Let's take this one, the 16.3 amps. Can we take it, guys, to the same table? Table 3, 10.15, B16, 60 degree column, 60 degree Celsius. What size conductor? One conductor number 12, A, W, G, T, H, H, N. That's the full answer. So I have two conductors number 10, Karen, and one conductor number 12. The neutral slightly less. The neutral slightly less. So these are the ungrounding conductor. Any question, guys, about the branch circuit for the 7 kW? The last thing we need to do for this baby, anybody knows what the last thing we need to do for it? Is go find the overcompression device. So I'm going to use, I'm going to find it. This will be, what is this? Is number, let's just adjust this one slightly. Question number 1E. And let's the E, what was the overcompression device? It's F. F is the overcompression device, is right here. I'm gonna make F right at the bottom here. Can you see it? So easy. You're gonna take the 23.3 amps, take it to 240.6. What size? 25 amp. So the next standard is a 25 amp circuit breaker. Your next standard is going to be a 25 amp circuit breaker. So you have a 25 amp circuit breaker. Any comments, guys? Any questions before we go into the second branch circuit? Second branch circuit. Okay, I'm actually gonna back of one step here. Everything is cool. I want you guys, I think I should not have applied this on the branch circuit. We don't want to apply it on the branch circuit now. So this one, the neutral conductor. Can you guys do the neutral? I apologize. The neutral conductor size is exactly the same. So it's 23.3 amps. Take the table 3, 10.15, B16, 60 degree column, and that will give you one conductor, number 10. A, W, G, T, H, H, N. I apologize. The neutral, we don't apply the rating factor for the neutral. I'm just reading I forgot, if you read the rating, the 70%, it does not apply to the branch circuits. So we're not going to do it for the branch circuits. Okay, so we're not going to do it for the branch circuit. So that one here would be basically right here. There you go. Can you guys adjust this one again? My apology. There's some So that would be for the neutral. E. So for neutral, we don't apply a neutral branch circuit. We don't apply the derivative factor based on. Let me put the thing here. Based on 220.61. 220.61. A or B, I believe. B. So when you come to the neutral for the branch circuit, can you guys not apply the 70% only for feeders and services? I thought so, but I don't know what I was drinking this morning. Okay, 23.3 amps. Can you guys see it's exactly like the HOTS? We just don't apply it because it's branch circuit. Okay, let's go do the same thing. So question number 1, we need to do G. So this is for G. Believe it or not, this is a G. Okay. If you guys look at G, we need to find the branch circuit for the 16 kW. So I have one 16 kW range. From the table 220.55 under C. Would you guys come up with the demand for one cable under C? 8 kW, right? One cable, one range under C, 8 kW. But except this range, guys, is more than 12. So you need to up this number. You need to up this number 5% for every kW. That range is more than 12. So that's step 1. Step 2, my friends, is you're going to take the 16 kW minus 12 kW, get you 4 kW. Then you take the 4, you multiply it by 5%. That will get you a 20%. Where did this came to be? This is from note number, these are the same size, note number 1. Note number 1, guys, in the table, in table 250.66, it will tell you to do so. Okay, the last thing you need to do is up that number so you can find your demand. So you take the 1.20, multiply this one by 8 kW, and that will get you 9.6. 9.6 kW. And gentlemen, this is the demand. Okay. Any comments, guys? Any questions? Any comments? Any questions? So then the next step is look at. Is it? All right, and circuits. A3, okay, where's A3? Okay. Okay. Any comments, guys, about this? So now we're going to find the amps. The next step is to find I equal 9.6 kW divided by 240. So if we divide this one, guys, by 240, what do you get? 40. Thank you. 40 amps. Even. Even. And then the rest is history. Now we're going to take your 40 amps. 40 amps. Take it to which table and why? 310.15 B16 column, 60-degree column. Why? They're not feeders to use the other table. So that will get you two conductors, number 8 AWG. THHN. That's it. Two hots. Does it make sense? Man, am I the one who is excited today or need more coffee? Okay. Now I told you we don't derate the neutral. And again, guys, the code, get used to the code. There's the rule and there's exception to the rule. Here's what the exception is. We don't derate the neutral, except if your range is more than 8 3/4, then you are allowed to derate it. The range that we did before was what? 7, so it was less than that. If your range is 8 3/4 or larger, you're allowed to derate the neutral, but you shall not use less than number 10. I'm going to write the right way you got this so you can think Chad did not bring this one from his phone. So that's the size. The second one is H, guys. H is for the neutral. We'll try the neutral. So the N conductor. I would like you guys to go to this this section, 210.19A3. 210.19A3 exception number, which exception is that? Exception number 2, I believe. Exception number 2. If you guys go there, so you don't really think I created that, which I tend to do sometimes. So exception number 2. Exception number 2. Can I guys get you to highlight this one? All the information I'm going to do is coming from that particular one. 210.19A3 exception number 2. It tells you if your range is 3/4 of an 8 kW and 3/4 or larger, then my friend, what you need to do is you can't have an overcomputation device less than 40, and you can derate the neutral 70%, but you cannot go less than 10. Okay, so let's go do that one. Apply that rule. Let's take the neutral. What was that? So I have 40 amps. 40 amps. Multiply this one by 0.7. Can somebody do that for me, please? What? 28. Thank you. 28 amps. Then you take your healthy 28 amps. You take them to which table? Table 310.15 B16, 60-degree column, and that will get you one conductor number 10. A W G T H H N. If you came up with less than 10, you have to use 10. Can I emphasize, and again, apologize, guys, the code is, there's a rule. That's why I said I thought that rule applied to all of them, that the exception only applies if the range is 8 3/4 or larger. Any comments, guys? Any questions? Any comments? Any questions about that? Comments, questions? 210, we got that one. So 8 3/4 and larger. So the 7 that before, it doesn't apply to it. That's why I got confused with where the application is. But here's the exception. You apply that rule. 1, number 10. So to wire this range, I need two conductors number 8 and one conductor number 10 for the neutral. the last thing we need to do is what? We need to find the hot, right? The overcap protection device. So for my overcap protection device, which is I. So here's my I. This is circuit breaker size. You take the 40 that you came up with, 40, take it to 240.6, that'll get you a healthy what? 40 amps. If you came up with less than 40, you must use 40. Because this range is more than 8 3/4. If you sit for your master exam, that's how did you catch you on that one. So in this case, 40 is your minimum for this range. If you came up with less than 40, you have to use 40. Any comments, guys? Any questions? Any comments? Any questions? So that's a range calculation. That's your range calculation. That's your range calculation. Any questions, guys, before we flip into so we finished the range calculation. We're going to flip into a box fill calculation. You guys want 5 minutes quick to, or shall I keep going? Let's take 5 minutes, huh? Then we flip into the box fill calculation. Okay, let me go ahead, guys, and start with the second question on the test. You guys have that, I gave you that one, right? Everybody has that diagram right in front of them. So do me a favor, have your NEC code book open to article section 3, 14.16, table 3. You need to be looking at table 314.16 A and B. That's where we're going to be. Okay, so here's what happened. We have a square box, a metallic square box. I drew that one with my graphic skills. See how good my graphic skills? So you guys are not going to see that. Tomorrow you're going to see the text like this, right? Here's what you're going to see. You're going to see a metallic square box, houses two cables, 14-2, NM cable, NMB cable, Romex, 2 number 12-2, and 2 number 10-2. And there are internal clamps, and I'm supposed to find the minimum square box size, as well as, first you need to find the minimum square box. After you find the minimum square box, you're supposed to find how many extra wires you can bring to this minimum square box. Did you guys hear me? That's a box fill calculation. First, size the box for these cables. So I drew them for you, so it makes it a little bit graphic. Here's what we have. We have 10-2, 2 10-2s, 2 12-2s, and 2 14-2s. And from table 314.16 B and A should get you guys all the calculation that you need. So you need to be able to go to 310.15, 314.16 A, that's for the box sizes, and B for the cubic inch for the cables. Okay. Any comments, guys, about what we do? So the first thing, Karen, that we need to do is find the minimum square box. Matthew, does it make sense? Minimum square box? Okay. So here's what we need to do. I'm going to use a color red. So I already wrote these for you guys to make it easier to move along. I have 2 conductors, number 10, 2 cables, 10-2, 2 cables 12-2, 2 cables 14-2. I need to accommodate for the equipment grounding conductor based on the largest conductor, which is 10. I need to accommodate for the clamps. All the clamps count as 1 based on the largest conductor. Okay, so let's start with the first set. For the 2 cables, 10-2, the first 2, can you guys see the first 2 is for what? The cables, 2 cables. The second 2 is for what? The 2 conductors inside the cable. Can you guys see that? The first 2 is for the cables, the second 2 is for the conductors inside the cables. And then after that, you need to accommodate, for the cubic inch. So then times 2.5 cubic inches. The 2.5 cubic inches, this number is coming from 314.16b. Okay? Then that's for number 10. For number 12, this number becomes 2.25. For number 14, this number becomes 2.0. Okay? 2.0. Can you guys see that? So I have two cables multiplied by two conductors in each cable multiplied by 2.5 cubic inches for every conductor. Everybody can see why I wrote them this way? The first two for the cable, the second two for the conductor, and the third number, 2.5, is the cubic inches for every conductor. The clamps, all the clamps count, Derek, all your clamps count as one based on the largest conductor in your cable, which is 2.5. All the equivalent conductor, and clamps, all of them count as one, all of them. The equivalent conductor count as one, all the clamps count as one based on the largest conductor in my system. What's the largest? Number 10. That's why I put 10 here, and that's 2.5, okay? The next, you need to add all these up. So when you add them up, you're going to end up, my friends, with 32 cubic inches. 32 cubic inches. When you add them up, you're going to end up with 32 cubic inches. Any comments, guys? Any questions about that? So you're going to multiply all these numbers, 2 by 2 by 2.5, 2 by 2 by 2.25, 2 by 2 by 2, 1 by 2.5, 1.24, add them all up. You end up with 32 cubic inches. 32 cubic inches. So that will be my 32 cubic inches. Okay, next. Any questions about adding them up? I give you. Anybody came up? Can you guys do the math? Somebody else verifying it? I got 32. Okay. Yeah, I don't know. Got 32. Okay. Anybody? How about Derek? Can you verify it for us while we're doing it? The next, guys, next step is very easy. Then next step is very easy. Then you need to take minimum box. For minimum box, you take the 32. You have to take it all the way. How much?
32.
32. Okay. You need to take it to 314.16a.
Is that the 68 one? I knew where that was, but where the
B.
wire size?
Right underneath it. Little table. Yeah, that's all right. Right underneath it.
All right.
Okay. So for 32 cubic inches, guys, I have table 314.16a will get you a size of a box. Here's the size of a box. 4 and 11 over 16 by 2 and 1/8. That's the size of the box from this table. That's the size of my box. Any comments, guys? Any questions? Very easy, straightforward, no gimmicks. Unlike the range calculation, there's a lot of jumping around. This one is really two tables, and they're straightforward. And the reason why I want to remind you, I am asking you for a square box. Derek, why did you go to square? Because I'm asking for a square box. Not octagonal, not a device box. I need you guys to solve a square box. The minimum square box that you can find. The minimum square box. So for 32, I have to go to the wider, bigger square boxes, and that will give me the sizes that you guys looking at. What was it? 32 here. I have to go all the way to the largest. That's the largest. Can you have thumbs up, Chad? How to do that, everybody? Adam, you're catching up here. Karen. Okay, so that's A. B, how many extra number 12 we can pull into this box? And I'm going to wait for a few seconds until Adam catches up with us, and then we'll go to B. Cool? Any comments, guys? Any questions? So you need to be able to go to 314.16B and A. Also, and A. These are for 16A and B. These two tables. And articles that tells you about the whole calculation. Any comments, any questions? Are there any devices in this box? No devices, nothing. It's a junction box. The clamps are inside. If the clamps are outside, big fat 0. Good? Okay. Now, remember, we sized the box. Now, I'm asking you for B, how many extra 12 not 14.2, and how many extra, 14.2, not 12.2, that you can pull into this box, okay? How many extra? 12.2 you can pull into this box, extra. 12.2 you can pull in this box, okay. The way you're gonna do it, guys, first go find the cubic inches for the box that you filled. What was the cubic inches for the box? 42 cubic inch. Everybody can find that from the table, from table 314.16a, it will give you 42 cubic inches, right? That's how much the box can handle altogether. How much cubic inches have we used so far? Right? For all the boxes. 32, right? Remember that 32, guys? 32 cubic inches already used. Where did I get the 32? I want to remind you guys that 32 were right here. All the stuff that we already sized for. Okay, 32 cubic inches. Extra, how much extra left? That piece of cake, subtract the two from each other. 42 minus 32, I have a 10 cubic inch extra that I can fill. Any question, guys, about this? The used is 32. The extra left is 10 cubic inches. The total is 42, right? Because the box is in the bigger than what we needed for, so there's still extra 10 in it. Now then, how many number 14 conductor can I bring into this? This is how we're going to do it. How many number 14? Then you're going to take the 10 and divide it by. Okay, now 14.2. How many conductors in a 14.2? How many conductors, guys, in the 14.2? Look at that, 14.2. How many conductors? 2. So here's the 2 for the first conductors. What's the allowance for every conductor number 2, number 14? 2. So they multiply this by 2. These together accommodate for the cable, because we're asking about cables. 14.2 means you have to have 2 conductors and 2 for the cubic inches, right? Because you can't have 1. Can you have a 14.1? There's no 14.1. You have to have 14.2. I'm bringing a cable, not a conductor. That's why you have to multiply the 2 here. The first 2 is for the 2 in the cable, and the second 2 for the cubic inches. Okay, so basically you're going to end up with 10 divided by 4, which that will get you a healthy, what's 10 divided by 4? 2.5 conductors. The conductors are going to be 2.5. Now, last time I checked, they don't make a 0.5 conductor cable. 2.5. These are cables, by the way. These are cables. Cables. Okay. Now, if you guys remember, they don't make, so a 2.5 cables of size, this is, so this will approximate into a 2 cables, because there's no 2.5, number 14, 2. So how many conductors, how many cables, number 14, 2 can I pull? I can pull 2 cables, number 14, 2. How many conductors? 2 times 2 is 4, right? 4 conductors. Any comments, any questions? So I can bring an extra 2 cables. Each cable has 2 conductors and terminate them right in that box. And I still meet the box fill calculation. Any comments, guys? Any questions? So that's how we use the boxes for this is used as a junction box. Any comments, guys, before we move into question number 3, which is ampacity calculation? Can I have thumbs up, Chad? We fully understand that one. Adam? Okay. Adam? All right. So let's go to question number 3. Question number 3, guys, talk about the ampacity of conductors. Ampacity of conductors. Here's the situation. I'm going to go read question number 3 for you from what we have. Okay, it says in an EMT conduit houses 2 conductors number 10 THHN conductors and 3 conductors number 4 THHN conductors and 4 number 2 aught, all THHN. All conductors are current carrying conductors. All of them are hot. Did you guys see it? All conductors are current carrying conductors. All conductors are current carrying conductors right here. They're hot. The ambient temperature is 40, so that's worse. I have all of them are hot, and their phases, and the ambient temperature is 40. We will find A through D. A, minimum current for number 10, minimum current and the overconduction device for number 10, minimum current for the 2 watt, and overconduction device for the 2 watt. You need to find the minimum current that each one of these conductors can carry, these two types. And what's the overconduction device you must land on it. Okay? Everybody can see that, what we're trying to achieve? Now this is a bad design. If you're to do it this way, the way we're doing it, that's a very bad design. To put all these conductors in one conduit, all carrying current. Really bad design. Okay, so I drew for you guys the 2 watt are the blue, and we have the number 4, THHN, are the red, and number 10 is the green. Just to identify, all of them are hot conductors, so I have 9 CCC current carrying conductors. The ambient temperature is 40. That's a worse. You should not do this. If the ambient temperature is like this, you shouldn't group them together. Did you guys hear me? It's not a good design. Okay, now how much current these conductors can carry under these circumstances? That's a question. Under these circumstances. I'm interested in 2 of them in particular. Okay, so let's go and start with my friend A. For A, the conductor is number 10. I have one conductor, number 10, THHN. I need somebody to go 310.15, B16, 60-degree column. Number 10 conductor, normal operating condition. Normal operating condition for number 10. How much current number 10 can carry under normal operating condition? 30 amps, right? 30 amps. Can you guys please go verify 310.15 B16 under normal operating condition. This is, I'm going to call it normal operating conditions. Normal operating condition, I feel sorry for who is going to read my handwriting here. Under normal operating condition, how much current this conductor can carry? 30 amps. Can somebody verify for me, please? It is. Okay, thank you. So if you guys go to the tables, 310, under normal operating condition, 60-degree column. Why 60-degree? I have no idea what the lugs are. I have no idea if it's what it's feeding, right? 100 amp or less is 60-degree column. 1 or smaller is 60-degree column. Okay. Now, are we under normal operating condition here, John? Are we? No, we're derating here. We're not under normal operating. So if this conductor was not, there's no derating whatsoever. I can pull 30 amps out of it and I'm good. But there's one little problem. I'm grouping it with multiple conductors and I'm putting it in a very hot environment. So you expect this to carry the same amount? No. Okay, so that's a normal operating condition. Now, obviously, we're not in a normal operating condition. So if you take then one could. So this is under your normal operating condition. Then you're going to take number 1 for derating purposes, THHN. For derating purposes, you're going to go to the 90-degree column. How much current number 1 can carry for derating purposes? 40 amps. The same table, guys. 310.15 B16. For derating purposes, number 10 can carry 40 amps. So why should I start with the 40 amps, not the 30? It's THHN, we're derating. Okay, so that's the second. So look at 2 amps. The normal operating condition 30, the abnormal operating condition, that conductor can be sized based on the 40. Okay, that's the second thing that you need to do. So here's 1, 2. The third one is derating. Now let's go derate. So you take your 40 amps, multiplied by, based on temperature, guys, what's the derating factor for 9 conductors? 9 carrying conductors. Thank you. 0.7 multiplied by, based on temperature, and I'm going to write where did this come from. You guys are very familiar with this. This number came from table table 310.15 3A. Did I do it right? B3A. 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 This is where this number came from for 9 carrying conductors. Then the second number, guys, is going to be 0.9.91. And this number came from table 310.15B2A. Okay? So now, do the math for me. Everybody knows where these numbers, one of them because of temperature, the 0.91. The ambient temperature is 40. Can you guys see the 40 ambient temperature? And the other one is 0.7 because of 9 carrying conductors. When you do your math in this paper, you end up with 25.5 amps. 25.5 amps. 25.5 amps. That's how much current this conductor can carry. How much current this conductor can carry under these circumstances? Can I guys get you? So I want you to look at this current. Under normal operating condition, this conductor can carry 30 amps. For the rating, we can start with 40. Because of we mix them up all together, now this conductor can carry no more than 25.5 amps. Cannot carry because of the ambient temperature. Because of the ambient temperature. Okay. So that's how much current this conductor can carry. Not 30, not 40, this amount, 25.5. So when you size your lights that you're going to be tying to this circuit, you're going to keep adding amps until you hit that number. Okay. Now B is for overcomputation device. B is circuit breaker. What circuit breaker do I need to land on this conductor? What circuit breaker do I need to land on this conductor? For the circuit breaker, guys, you take the 25.5 amps, you take it to 240.6, and you go down to 25 amps. So your conductor size, the overcomputation device here can be 25 amps. Your conductor here can be, what was it, number 10? This is a number 10. Number 10. And your load here, right? Your load here cannot be more than 25.5 amps. Cannot be more than 25.5 amps. And obviously, if this is 25, it will limit the load to 25, right? The load already 25.5, but if I put the circuit breaker 25, I'm limiting the load actually to even less than 25.5. Any comments, any questions? Any comments, guys, any questions? So we went down an overcomputation device. Now I'm going to warn you, you go down an overcomputation device if your equipment is like your feeding receptacles and things are plugged in. If you're feeding things that's fixed, you can go up on the circuit breakers. But let's leave that one to a different topic. So we went down to 25, assuming these are receptacles. You know, if you're feeding receptacle circuit or something, or plugged-in lights, where you can plug external in, you can go down to 25. So what's the circuit breaker size? Take this number, drop it down to 25. Any comments, guys? Any questions? Now let's do the same thing for the second conductor. We're repeating ourselves, guys. Now the second conductor was what size? We're doing question number 3 for C. For C, I'm asking you, gentlemen, to find one conductor, 2 watt, THHN. Under normal operating condition, table 310.15B16, that will be, which column do you go to find the normal operating condition for 2 watt, and why? 75. 75 normal operating condition for this conductor. 75 2 watt, right? Is it 2 watt? 75, that will give me 175. 175 amps. If I am not derating, If I'm not derating, that's how much current this conductor can carry. Done. Piece of cake. Now I have one little problem. I am derating. So I'm going to go here, take the one conductor, 2 watt, T, H, H, N. I'm going to take it to the same table except 90-degree column because of the rating table 310.15 B16. If you guys go to the 90-degree column for this guy, 195 amps, am I right? 195 amps? 2 watt, 195 amps. Why do I have to start? Why can I start with 195? Because I'm derating. Okay. So then the rest is history. Now you come over here and you take the 195, you multiply it by 2 deratings. Number 1 is 0.7 because of bundling. Number 2 is 0.9 because of temperature, and you end up with 124.2 amps. That's how much current this conductor can carry. That's how much current this conductor can carry. Now, Derek, I want you to look at this. Look at the normal operating condition for the conductor. 175. I dropped it down to what? 124.2 because I stupidly plug it into a conduit, group it together with other conductors in a very hot and very 40 degrees Celsius is hot. Okay, so I dropped 50, almost 50 amps. I can't use 50 amps on the same conductor. So that's a bad application for a conductor. A conductor like this should not be grouped with others. You should probably put it in its own conduit. Okay. So the last thing, guys, is D. D is the overcapacity device. We need to find the overcapacity device, so that's D. My circuit breaker, which is going to look something like this, and here's my load at the end. Okay, now remember this is a 2 watt. Okay, and the load is 124.2. The load here, I need the circuit breaker at the top. For the circuit breakers, guys, you take the 124.2, you take it to 240.6, and now here you can go down. So I can go down here, and when I can go down to 110 amps, right? I can go down to 110 amps. If this conductor is feeding things that can be plugged in, portable plugged in stuff, but you can also, and that's where it gets confusing, that you can go up to 125 amps. And I'm gonna put the for the test guys go down. But in real life you can go up based on 240 dot let me get that article. 240 dot something. Okay, here we go. Overcapacity. This will be 240. 240.4 240.4 B 240.4 B. If you guys go to 240.4 B, it will tell you that if you hit a non-standard, if the conductor ampacity is non-standard like this, can you see 124.4 is not a non-standard, you can go to the next standard up, which is 125. Except if you're using assemblies where you're plugged in. Like for example, receptacle like these. If I have a branch circuit and I'm feeding all these receptacles, I can't go up. Because people can increase the load and plug the load at any time. If I'm feeding a panel, then I can't go up. Okay, so for the test, if you guys go down, that's fine with me, but to understand it fully as we move through, this is what applies, 240.4 B. But for example, this 4 out most likely is going to be a panel, and we go up. I mean, do you see a receptacle is fit from a 2 watt? So, any comments, guys? Any questions? So I can go 110 amps down because it's not standard for the circuit breaker. So I'm going to go size it based on the 100. So this will be 110 amp circuit breaker, 2 watt, and it limits my load to, my load is 124. So I'm limiting this one is lower than 124. If you put a 110 circuit breaker, can you pull 124 amp out of it? You can't. This will trip. Then what do you do? What do you do, guys? Then what you do is you limit that load, lower that load into 110. Any comments, guys? Any questions? How to size a conductor, the ampacity of the conductor, and the overconduction device. For the test, please go down. When you go, size based on now. Though you can go out. When do I go down and when do I go up? You go down if you're feeding dedicated loads. You go up if you're feeding dedicated loads. You go down if you're feeding multi-outlet assemblies and plugs and so forth. The portable loads can be plugged in, and the reason for that one is because can you control what's going to be plugged in these? Do you have any control what's going to be plugged in these receptacles? I have no control. Do I control what's going to be plugged in the circuit that's feeding these lights? Yes. Do you think an average Joe can climb in here and to the junction box and go tie a lighting circuit to this junction box? Should not do that. Might as well bust the door then. But an average Joe can walk in here and plug anything in these outlets, right? That's meant for average Joe. Do you guys see that? If it's open to the public where people can plug in, you have to go down. If it's not open to the public, like all these lights above the spinning ceiling, you should not mess around with the circuit. Then you can go on. Okay, last question. Any comments, guys, before we do the last and the easiest one of all? The last one is very easy. Any comments, any questions? Okay, so we found this one. Now the last question, guys, is this is going to be for you guys. These are panels, very similar to the project that we're sizing. Very similar to the project that we're sizing. I can't emphasize, it's very similar to the project that we're sizing. And we're asking you here, go back to the thing. It says a 400 amp main panel powers one 350 panel, 175 panel, 125 panel. The power system is 240, 120 single phase. That powers a dwelling unit. Find the minimum service entrance conductor size for the 400, minimum feeder conductor size for the 350, and for the 175 and the 125. So we need to size the minimum service conductors for all these services. Okay, so piece of cake. This is the easiest probably. So this circuit is 350. This one is 175. This one is 125. All of them are 240, 120 dwelling. So you're going to go to table, straightforward, you're going to go to table 310.15 B7. Size everything. Okay, so I'm going to go to A and put them right in here. Start with A. For A, guys, if you take the 400 amp, take it, I'm going to write the table one time. Table 310.15 B7, because it's dwelling. I'm going to end up with, I can derate the neutral. But I have no idea what the sizing of the neutral. So in this case, I'm pulling a full neutral for this example. So I have 3 conductors, Y3, 2 hots and a neutral, full neutral. Each one of them has 400 kcm. That's it, done. Just picking them up to the table. 400 kcm THHN. This is for the service. A. B. For B, guys, 350 amp, same table. I'm not going to write the same table. So 3 conductors, each conductor is number 350. 350 kcm THHN. And ABC is 175 amp, same table. That will get you 3 conductors, number 1 aught, A, W, G, T, H, H, N. And the last one, A, B, C, D, is 125 amp, and 3 conductors, and the size is number 2, A, W, G, T, H, H, N. Done. That's it. So this is just straightforward using that table. I want to warn you guys, I pulled from neutral here. In reality, we can derate the neutral. We could derate if we know what the unbalanced load, I can size based on the unbalanced load. Later on, when you size with me, the only thing that would be different, man, is the size of the neutral will be slightly less. But for the sake of this exercise, I'm okay with this. Okay? All right, so that's it for the calc. I want to remind you, not warn you, but remind you guys, there's a lot of calculation we're going to do through the year. Write yourself a cheat sheet, bring it with you. If you're confused which table to go, or am I going to go up or down, raise your hand. I'll be more than happy to give you a hint. Am I going to go up on this circuit breaker or down? Write the steps, where to go. You're engineers and designers. You're sitting in an office, at a desk in an office, and minding your own business and designing. Have all your tools handy. But I want you to know how to do it, though. Okay? All right, shall we take 5 minutes, and then I'm going to go just 10 minutes over after that, over the theory. We have a theory, just 10 minutes over what's going to be in the theory, and then we're done.